Okay, I hope everybody's having a good day today. Today we're going to continue on our study of AC circuit analysis, and specifically we're going to be looking at RLC parallel circuits. Up to this time we've looked at RC series circuits, RC parallel circuits, RL series circuits, RL parallel circuits, RLC series circuits, which was done in two parts. One was kind of a theoretical introduction to it. The other one was an analysis where we took a problem and we solved for several quantities in that. And then today what we're going to look at is RLC parallel circuits, as I indicated. And the configuration of an RLC parallel circuit is pretty straightforward. You've simply got a resistor that's connected to a source, and for our purposes obviously it's going to be a sinusoidal source. That's in parallel with a capacitor or an inductor. It doesn't matter the order. And then lastly an inductor, and we're going to make our inductor an iron core inductor as we've done all along. So our resistor is going to be labeled R. Our inductor is going to be labeled, our capacitor is going to be labeled C, and the unit of energy storage capacity of a capacitor is in what units? Anybody remember? Farads, right. So we measure the energy storage capability of the capacitor in farads, and then of course we have the opposition to current flow associated with that capacitor, which we call capacitive reactance, X of C. And from previous discussions, X of C is found by using this formula, 1 over 2 pi times the frequency of the source times the energy storage rating of the capacitor in farads, or microfarads, or millifarads, or nanofarads, or whatever unit of farad you have. Okay? And then lastly, we have our inductor, and our inductor is measured in terms of energy storage capability in what unit? The Henry, right, Henrys. So our inductor is measured in units of Henrys, and then there is an opposition to current flow associated with that inductor. And the formula that we've used all along is that the opposition to current flow, or the inductive reactance of that inductor, is found by using the formula 2 pi times the frequency of the source times the energy storage rating of the inductor in Henrys. Okay? And so you'll notice really the only difference between these two formulas here is that one is an inverse, the other is directly proportional, and then of course one has farads in it and the other one has Henrys in it. Okay? And of course you'd want to have that on your reference sheet so that just in case you forgot it, you would be able to refer to it. Okay. Now for this particular circuit, we're going to give the source a voltage. So we're going to call that the source voltage E sub t. And let's go ahead and give that a value of 15 volts. And let's give the frequency of our source a value of 300 cycles per second, which is measured in hertz, H-E-R-T-Z, abbreviated H-Z. Okay? Now, the thing that makes this particular circuit easy and hard is the fact that basically it's a parallel circuit. Okay? In a parallel circuit, it's very simple to look at the circuit and see what is the same everywhere. Okay? So when we look at this circuit and we realize that we have a closed loop here, 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 no matter which closed loop we look at, we have only two components in that closed loop. Okay? And so by Kirchhoff's voltage law, that tells us that the voltage across every component, including the source, the resistor, the capacitive reactance and the inductive reactance is going to be what? The same. In other words, the voltage doesn't change. So by inspection, just looking at the circuit, we know that if this is 15 volts, then we'd measure 15 volts here, 15 volts here, 15 volts here. Okay? So if we wanted to draw a vector diagram, which represented the voltage, we've already said that the voltage of the source is equal to the voltage drop across the resistor, which is equal to the voltage drop across the capacitor, which is equal to the voltage drop across the inductor. Okay? And so it's really just a trivial exercise to draw a vector diagram, because all you're doing is just drawing arrows on top of each other. So there's the arrow that represents this guy. Here's the arrow that represents this guy. Here's the arrow that represents this guy. And then finally, here's the arrow that represents this guy. So in other words, they all have the same magnitude and they all have the same direction. Okay? And so by inspection, we can look at that circuit and we can immediately know that the voltage is the same everywhere in terms of magnitude and phase. And it almost becomes a waste of time to draw a vector diagram, because we're just going to look at a straight line. Okay? But I just want to point that out to you, because the other vector diagrams that we're going to look at, like the current vector diagram, the power vector diagram, the impedance vector diagram, they're not going to be straight lines. Okay? They're going to ultimately form right triangles. Okay? And from those right triangles, we're going to be able to figure out what's going on in the circuit. Okay? And so I'd like everybody to have their books handy, because this is a good opportunity for you to compare what I'm going to derive for you on the board and what is in the appendices of your textbooks. Okay, because it's a good place to go if you forget it or you don't have it written down on your cheater sheet. Okay? All right, so what I'm going to do is, now that we've established the voltage is the same everywhere, I'm just going to erase this, because by inspection we know that the voltage is the same here, 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 and here. Okay? Now, if we gave values to these components for analysis purposes, why don't we have somebody give me a value for the resistor, just to show you that it doesn't matter what value it is, the procedure's the same and it all works out. So somebody give me a value for the resistance. Okay, so we're going to go with 47 ohms for the value of the resistance. How about the capacitive reactance? Let's not go wild so that we have little tiny vectors and big giant vectors. You know, let's make it, you know, plus or minus, say 50% of what you gave me for the resistor. But just give me some arbitrary number. 22. Okay, so the capacitive reactance is 22 ohms. Okay? And then what about the inductive reactance? Somebody give me a value for the inductive reactance. 75 ohms. Okay? So we're going to give this guy a value of 75 ohms. And the reason that I do it this way, rather than coming in here with a pre-worked problem that I just write on the board, is to show you that the scientific method works no matter what the values are. Okay? Now obviously these values would have been a function of the frequency and the capacitance rating in farads and the inductive rating in henries. So if we wanted to figure out what the capacitance had to be if the capacitive reactance was 22 and the frequency was 300, then we'd have to go up to this formula and we'd have to solve that formula for C, right? And then we'd plug those numbers in and we'd figure out what value of capacitance or energy storage rating for the capacitor would give us a capacitive reactance of 22. Does everybody see that? Are there any questions about that? Okay, that should be pretty straightforward. And then likewise, if we have an inductive reactance of 75 ohms, the actual energy storage rating of the inductor, right, is a function of the frequency of the source, which we said was 300, okay, and also a function of the inductive reactance that we chose arbitrarily. So what we could do is we could solve this simple algebraic formula for inductance in henries, and then we would just plug in 300 for F, and we would plug in 75 for X of L, and then that would give us a value in henries. Everybody understand that? Okay. Is there anybody who doesn't understand that? Okay, good. All right, so now we have a bona fide RLC parallel circuit. And the first thing I'd like to do is I'd like to take a look at, well, the first thing we did was the voltage. We found out the voltage was the same everywhere. Second thing I'd like to do is take a look at the current, okay? If we look at the current that's flowing from the source, so we'll call this I sub t. Your book likes to call that the total current, meaning the current from the source. Some books will call that I sub s, meaning source current. Some books will call it I, and then they'll write out S-O-U-R-C-E, I source. It all means the same thing. It's the current that's flowing out of whatever your power generating active element is. And that could be a function generator on your workbench, or it could be a power plant. Fossil, geothermal, wind, solar, nuclear, doesn't matter, okay? And one other thing that I want to emphasize, which I've done previously several times, but I want to emphasize what the 15 volts represents. If we haven't marked that the voltage is other than RMS, then what do we assume that the voltage is rated at? Is it a peak-to-peak voltage, an average voltage, a zero-to-peak voltage, an RMS voltage? RMS, right. So if it were a peak-to-peak voltage, it would look something like this. The total voltage is equal to 15 volts, and then there would be a little P dash P. And that would tell you that that was a peak-to-peak voltage, okay? If you take away the P to P, then the industry standard is that that's an RMS value, okay? If you wanted to, you could write in RMS, okay? But it's just understood by definition that this is RMS, so we don't bother writing it in, okay? I just want everybody to be aware of that, okay? So let me go ahead and erase that. Now, there are several things that we can do with regard to the current that's flowing in the circuit, which go all the way back to the second week of this class. Just like I talked about, Ohm's law will be used over and over and over again. We're going to use Ohm's law to solve a large part of this circuit, okay? If I know what the voltage drop is across this resistor, and I know what the opposition to current flow is of this resistor, then is it fairly simple for me to calculate what the current is that's flowing through the resistor or up to the resistor? It would be E over R. So the current that's flowing into the resistor is equal to the voltage drop across the resistor, which we've already said is the same here, 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 and here, divided by the opposition to current flow of the resistor, which would be the resistance, okay? And so if everybody will get their calculators out, I'm going to be counting on you to kind of keep up with me, because I didn't pre-work this problem. I had you arbitrarily give me numbers. So the voltage here is obviously 15 volts, RMS, and the opposition to current flow is 47 ohms. And so that gives us a current that's flowing up to the resistor of how much? 15 divided by 47 is what? 0.319 amps. Okay? And we could round that to probably 0.32, and we would get the accuracy that we're looking for. So we'll just go ahead and do that to make our lives a little easier. So there's 320 milliamps that are flowing from this node up to the resistor. Now, it's an important thing to realize that when the current that's flowing from the source reaches this point or node in the circuit, there's a branch. In other words, the current can split off, and that's exactly what it's doing. Part of the current is flowing up through the resistor, and part of the current is continuing on to the rest of the circuit. Okay? Now, the easiest way to figure out what the rest of the current is that's continuing to the circuit is to look at each component independently. Why? The reason is because we already know its voltage. We know the voltage is the same here, 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 and here. So the same technique that we use to find out that the current flowing through this resistor is found by Ohm's law, which is E over R, we got 0.32 amps or 320 milliamps. Okay? If we wanted to figure out what the current was that was flowing up to the capacitor, could we use a similar approach? Very similar formula, but the difference is going to be that the current that's flowing up to the capacitor is going to be the voltage drop across the capacitor, which we know is 15 volts, divided by not R, but what? The capacitive reactance, X of C. And the reason we have to use capacitive reactance and not capacitance is because capacitive reactance is measured in what unit? Ohms. Okay? So the only way we can use Ohm's law is if we're dividing by ohms. We can't be dividing by farads. Okay? We had to convert farads into ohms using this formula. Okay? Which is effectively what we did. Okay, so calculator's ready. We have 15 volts across the capacitor divided by the opposition to current flow associated with the capacitor, which is 22 ohms, which gives us a current flow to the capacitor of how many amps? 0.68 amps, or 680 milliamps, however you want to look at it. Okay? And then, in a similar way, the current that's flowing to the inductor, or the current that's flowing here, we'll call this I sub L, current that's flowing to the inductor is simply going to be equal to the voltage drop across the inductor divided by what? The resistance of the inductor? The inductive reactance. The inductive reactance. And we call that X of L. And remind me again why it is that we can't use the energy storage rating of the inductor? Because it's measured in henries. It's measured in henries. And Ohm's law does not give us a formula where we can take voltage and divide it by henries. Okay, that would be a nonsense answer. It wouldn't mean anything. Okay? So when we plug those numbers in, and again, this is just simple Ohm's law. Okay? When we plug those numbers in, we have 15 volts across the inductor by Kirchhoff's voltage law, divided by the inductive reactance of the inductor, which is 75 ohms. So what do we get when we take 15 volts and we divide it by 75 ohms? 0.2 amps, or 200 milliamps, okay, however you want to express it. So now we can see that the current that's flowing to the resistor is 0.32 amps. The current that's flowing to the capacitor is 0.68 amps. The current that's flowing to the inductor is 0.2 amps. Okay? And so from that, we can develop what we call a current vector diagram. A current vector diagram. And with a current vector diagram, what we effectively end up with, once it's simplified, is a right triangle. Okay? Now, the reference arrow of our right triangle is always, always, always going to represent, if we're talking about a current vector diagram, the current flowing through which component? The current flowing through the resistor. So this is the current flowing through the resistor, and using Ohm's law, we calculated that that was 0.68 amps. So this is 0.68. Oh, I'm sorry. Thank you. I was looking in the wrong spot. Wouldn't that be beautiful to get that on tape, right? Okay? All right. So the current flowing through the resistor is 0.32. The current flowing to the resistor is equal to 0.32 amps. Thank you for my oversight there. Okay. Now, it turns out that when we represent the current vector diagram and we represent the current that's flowing to the capacitor, in the raw form, we end up with a vector that's pointing downward at an angle of 90 degrees relative to our current, the resistive vector diagram, or the resistive vector, should I say. Okay? When we plot our vector that represents the current flowing to the inductor, we end up with a vector or a line that's pointing up. Okay? Those two lines are how many degrees apart from each other? 180 degrees. They're 180 degrees. And so that allows us then to simplify this by drawing one vector diagram pointing upward. If you look at the current and you look at the inductor, you can see that the current to the inductor is less than the current to the capacitor. Okay, it's less than that. So let's go ahead and do it the long way, just for the sake of completeness. Let me get some room here. This is 0.32 amps. Okay? So if we draw a vector that represents the current that's flowing to the capacitor, I sub C, that's going to be equal to 0.68 amps. Correct? Yes. 0.68 amps. And then if we draw a vector that represents the current flowing to the inductor, that's going to be an arrow pointing straight up. So there's 180 electrical degrees between these two vectors. This is 180 degrees, okay? But the current that's flowing to the inductor is equal to 0.2 amps, okay? When you look at that vector diagram, it's clear that there's a 90-degree angle between the resistance and the inductance, a 90-degree angle between the resistance and the capacitance, and then of course 180 degrees between the inductance and the capacitance. Okay? But because these two guys are at 180 degrees, we can simplify them, okay, by subtracting them out. Now, if we want to do this graphically, which is what I'm going to do right now, I'm going to do this graphically, we are going to end up with a triangle that's pointing down, right? Because if this is 0.2 and this is 0.68, then if we simplify these two vectors, because they're at 180 degrees, then the resulting vector is going to be 0.68 minus 0.2. Are you with me? How many of you follow me? Good, good. Okay. So what we're going to do is we're going to take this vector right here, and we're basically going to get rid of it. Are we getting? Yeah, absolutely. Okay. Okay. All right. Okay. So let's transcribe everything over to this board right here. I'm going to go ahead and just quickly redraw the circuit. We had a resistor in parallel with a capacitor, which was in parallel with an inductor. Okay, and this guy was 15 volts, which means there's 15 volts everywhere, and the only thing that I'll draw are the currents. So the current that we found flowing to the resistor was equal to 0.32. The current that we found that was flowing into the capacitor turned out to be equal to 0.68, and the current that was flowing to the inductor turned out to be equal to 0.2. And of course, these are in amps. These are all in amps. Okay? And so what we were doing was identifying our current vector diagram. Okay? Our current vector diagram. As has always been the case, regardless of whether we're dealing with RC series circuits, or RL series circuits, or RL parallel circuits, or RL series or RC series circuits, our reference vector is always going to be the current flowing to the resistor. Okay? So the current flowing to the resistor we calculated previously using Ohm's law, and we found that the current to the resistor was equal to 0.32 amps. Okay? We found that the current that was flowing to the capacitor, which would be a vector pointing down with respect to the reference vector. Why is it pointing down? The reason it's pointing down is because of the formula x of c is equal to 1 over 2 pi frequency capacitance. It's a negative imaginary number. We won't get into the mathematics of it, but because it's an inverse, it's going to point down, okay? And so the current that's flowing to the capacitor is equal to 0.68. And then if we want to draw the complete current vector diagram, we have to represent the current that's flowing to the inductor as an arrow that's pointing up, or at 90 degrees with respect to the current vector, or the current that's flowing to the resistor, and 180 degrees with respect to the current that's flowing to the capacitor. Okay, and we found that that current was 0.2. So the current that was flowing to the inductor was equal to 0.2 amps. Okay? Now, because these two vectors right here are 180 degrees out of phase with each other, in other words, one's pointing straight up, the other's pointing straight down, so they're kind of, canceling each other out. In other words, if they were both the same magnitude, they were both 0.2 amps, they would disappear. They'd go away, okay? They wouldn't physically go away, but in terms of our current vector diagram, they'd cancel each other out, okay? Now, as we're doing our vector analysis, because this is 0.2 pointing up, which is a smaller number than the current flowing to the capacitor pointing down, then what we can do is we can eliminate the vector that's pointing up, and we can reduce the vector that's pointing down by how much? 0.2. Okay? So if we eliminate this vector right here, all we're doing is a simple algebraic operation, then this is going to be 0.68 minus 0.2, which is going to be 0.48, right? Okay? So this is going to shorten up because of the current flowing to the capacitor, and the number here is going to change from 0.68 to 0.48. The reason, again, is because those two vectors were 180 degrees out of phase with respect to each other. So I'm going to go ahead and erase this so it's not too cluttered, so that we can see our current vector diagram. Now, there's an interesting thing that's happening here, and that is that we have a triangle where the vertical component of our triangle is pointing down, not up. Now, there's nothing wrong with that. It's just that in industry, we rarely see that. Can anybody guess where you would see that? Can anybody guess where you would see a vector like this? A factory? One that I can think of off the top of my head is a factory that manufactures and tests capacitors. Okay, because their load would be predominantly capacitive. Okay? Or the reactance of their load would be capacitive reactance predominantly. Okay, so just for the purpose of making the triangle a little easier to deal with, I'm just going to make this vector a little bit longer, and I'm going to shorten this guy here, I sub r, only so I can draw the hypotenuse of the triangle. Now, when I draw the hypotenuse of the triangle, what is that going to represent? Any ideas?
True power.
No, this is a current vector diagram. So it's got to measure a current.
Total current.
Total current. So it's going to be the current that's flowing from the source, which could be a pad mount transformer, or it could be a function generator on your bench. Just depends on what you're doing, what your application is. But if we draw a hypotenuse here of this triangle right here, this is going to represent the current that's flowing from the source to the rest of the circuit. Okay? Now, what I'd like everybody to do is to open up their textbooks, look in the appendix for RLC Parallel Circuits. You can hold on. For RLC Parallel Circuits. Okay? And I would like you to see if you can find a formula for I total, or the current that's flowing from the source into the rest of the circuit. and then we're going to compare that to what we've just done to see whether or not it matches up. As soon as somebody finds the page, why don't you shout out the page number? It should be back around page 1070, very back of the book. Anybody having luck?
Yeah.
Okay, what is the formula that you're looking at?
Total current equals the square root of
Total current is equal to the square root of
resistor current squared
the current flowing through the resistor squared plus
IL minus IC squared.
the quantity current through the inductor minus the current through the capacitor quantity squared. Okay? Now, let's go ahead and plug the numbers that we have so far into this formula and then compare it to the vector diagram that we developed. The current to the resistor was equal to 0.32 amps. So the current to the resistor is 0.32 amps, quantity squared, plus the current in the inductor. This is the original inductor current, which was 0.2. So that's 0.2 minus the current into the capacitor. And the current in the capacitor we found to be the current in the capacitor was 0.68. So this was 0.68. And just for room's sake, I left the unit out on this, but this would also be in amps. Okay? And this is squared. Okay, now notice something interesting here. We took 0.2 and we subtracted 0.68. My question to you, is that the same thing as what we did with this vector right here? Yes. It's graphically the same as what we did with this vector right here. Okay? So what I'd like you to do is put that in your calculator and tell me what the result is of this calculation. Square root of 0.32 squared plus quantity 0.2 minus 0.68. We're going to get a negative number, but when we square it, it'll become positive. Right? Because anything times itself is a positive number. Okay? Two negatives multiplied together. I'm sorry, not anything times itself. That's a misstatement. Two negative numbers multiplied together is positive. So what do you get? 0.576. Okay, so we get 0.576 amps. Okay, that's the current that's flowing from the source. Okay, now I want you to notice something that's very important. Okay. You can do the problem either this way or this way, but if you have the formula and you understand how to use it, it's a lot easier to just plug the numbers into the formula. Okay, I was doing the actual vector diagram just to show you the interrelations between the current vector, the vector representing the current through the inductor, the vector representing the current through the capacitor, okay? And how these two guys cancel each other out to some degree. Maybe not totally, but to some degree they cancel each other out. And you can see that that's happened here, right? Because this is a subtractive process, and then we end up with a negative number, but it really doesn't make any difference because when we square a negative number, what do we get? A negative or a positive? A positive number. So we're adding two positive numbers, okay, and then we're taking the square root of that, which would be the same thing as if we use the Pythagorean theorem here. We would be taking the square root of the sum of the squares of two positive numbers. Okay, so it's the same thing. Now, the thing that I want you to recognize is a mistake that some folks who are just starting out in this make, and that is to treat this as an algebraic process and not a vectorial process. This is vector analysis, okay? If we had, let's just say, hypothetically, a DC circuit with a DC power supply, okay? And I told you that there was 5 amps here, 5 amps here, and 5 amps here, then how much current would be flowing from the source? If I said there was 5 amps here, 5 amps here, let me draw it. Right. So if I had 3 resistors, 1, 2, 3 resistors, and I said this guy was 5 amps, this guy was 5 amps, and this guy was 5 amps. Then the total current flowing from the source would be 5, 10, 15 amps, right? 15 amps. And that would be accurate, okay? Now, because of the fact that we have an out-of-phase condition, in other words, the resistor, capacitor, inductor are out of phase with respect to each other, we can't treat it the same way that we did in the DC analysis. We have to treat it differently, okay? Now, let's just say for a second that somebody thought that they could treat this circuit the same way that we treat a DC circuit, where everything's in phase. Let's just see what we'd get. If we thought, let me just erase this. If we thought that we could take the current in the resistor, so the total current was equal to the current in the resistor plus the current in the capacitor plus the current in the inductor, that means that we would get 0.32 plus 0.68 plus 0.2. And obviously these are all in amps. What does that come out to? 1.2? That comes out to 1.2 amps. Everybody agree with that? Okay. Can you see that there is a huge difference between down here what we calculated using vector addition, which was 0.756. We're comparing that to 576, and we're seeing that those numbers are very different from each other. This number was derived assuming that nothing was out of phase. This number is incorrect because it's derived using an algebraic approach. This number is correct because it was derived using vector analysis. So the current that's flowing from the source into the rest of the circuit is 0.576 amps. And you can see that at first glance, it doesn't make total sense, because when you look at the current that's flowing into the capacitive branch of the circuit, and you compare it to the current that's flowing from the source, which one's bigger? The capacitive. So what that tells you is there must be an energy exchange between the capacitor and the inductor that is not reflected back to the source. In other words, they're playing patty cake with each other, so to speak. There's an energy interaction between the inductor and the capacitor, and what's happening in reality or in physics is the collapsing and expanding magnetic field of the inductor, okay, is supplying current to the charging and discharging electric field of the capacitor. Okay? That dance that happens between these two components is stuck in this loop right here and does not transmit itself back to the source. That's why the source can have less current flowing than the current that we see flowing in the capacitive branch of the circuit. That's an example of why power factor correction works, why power factor correction lowers the total current that the utility has to deliver to your plant, and thus the total current that your meter is registering, and subsequently the total bill that you're paying for the electricity that you're using. Okay, so if we were to do a power vector diagram, we would have watts, vars, and volt amperes, right, for our reference vector, our vertical vector, and our hypotenuse. And then for our impedance vector, we would have resistance, capacitive reactance, inductive reactance, and then the total ohms would be called what? Impedance. And what letter do we use to designate impedance?
Z.
Z. Okay, so we would do it using the same approach, it's just that the units would be different and the numbers would be different. Okay? I can see that we've run out of time for today, so if you have any questions that you need to talk to me about independently, come on up and see me. Otherwise, have a safe drive. Good night.
Thank you.